The tropical oceans function as the Earth's largest solar collector, absorbing radiation across millions of square miles. While solar and wind energy provide significant renewable capacity, they are intermittent, fluctuating with weather patterns and diurnal cycles. Ocean thermal energy conversion, or OTEC, addresses this limitation by providing baseload power. Unlike atmospheric renewables, OTEC utilizes the thermal inertia of the ocean to generate electricity 24 hours a day, regardless of surface weather conditions or time of day. OTEC operates on the Rankine cycle, driven by a temperature gradient between the ocean's surface and its depths. A minimum temperature differential of 20 degrees Celsius is required for viable energy extraction. In typical tropical regions, surface water reaches 25 degrees Celsius, while water at a depth of 1,000 meters remains near 5 degrees Celsius. The process begins by pumping warm surface water into an evaporator. Inside, it heats a working fluid, typically ammonia, which possesses a low boiling point. As the ammonia vaporizes, the resulting high-pressure gas expands through a turbine connected to an electrical generator. To complete the cycle, cold seawater is pumped from the deep ocean into a condenser. This cold water absorbs heat from the ammonia gas, reverting it to a liquid state for reuse. This continuous loop converts thermal energy into mechanical work through fluid expansion. Engineering approaches to OTEC vary based on the treatment of the working fluid. The closed-cycle system is the industry standard, utilizing substances like ammonia in a sealed loop to maximize heat transfer efficiency. Alternatively, open-cycle OTEC eliminates the secondary working fluid by using the seawater itself. In this configuration, warm surface water is placed in a vacuum chamber where it flashes into low-pressure steam to drive the turbine. A critical secondary finding of open-cycle systems is the production of desalinated fresh water. When the steam is condensed using deep-sea water, it yields high-purity water as a byproduct. Hybrid cycle systems combine these methods, utilizing the ammonia cycle for power while simultaneously producing fresh water. These configurations offer high utility for island nations requiring both energy and potable water. Despite the vast energy potential, OTEC faces significant thermodynamic and structural challenges. The Carnot efficiency of the system is mathematically limited by the small temperature delta, resulting in a net thermal efficiency of only 3% to 4%. Consequently, OTEC plants must move massive volumes of water to produce significant wattage. The primary infrastructure hurdle is the cold water pipe. Reaching the required 5 degrees Celsius water necessitates a conduit extending approximately 1,000 meters vertically. These pipes must withstand extreme hydrostatic pressure and corrosive marine environments while remaining flexible enough to survive surface wave action. Constructing and mooring these pipes represents one of the most complex structural engineering feats in renewable energy. OTEC represents a stable, 24-hour renewable energy source that leverages the ocean's thermal mass. While the engineering requirements for deep-sea extraction are intensive, the dual output of baseload electricity and fresh water makes it a critical technology for tropical maritime regions.